iteration, that is in the third time, if you pick a sock, it will, there's a perfect chance that you will, there is 100% chance that you will be getting a matching pair. Okay, so with a half probability, so it with the moment it is decided, so the number of attempts is decided at this moment. Okay, so if it is black, that is with a probability of half, then it will be done with a 3 attempt. The probability that it will be done in 3 attempts is also half. The probability it will be done in 4 attempts is 0, because either you will do it in 2 attempt or 3 attempt. So when is it decided? It is decided in the second attempt itself. If you get a R, that's okay, it is done and dusted there. But if you get a black, then it is for surety that you will get it in the third attempt, right? So the expected number of attempt that is required will be 2 with a probability of half and 3 with a probability of half. Okay, so the answer to this particular question is 2.5. Okay, so this is again an easy question. Now let us discuss this particular question. Okay, so a coin making machine produces pennies. Each penny is manufactured to have a probability P of turning up tails. Okay, so we this company makes coin, and the probability that you get a tail is P in this. So the probability that you get tails in this particular coin is P. Now the thing is, this P is not a constant stuff. Okay, so this P is taken randomly from a uniform distribution of 0.1. What is uniform distribution? The probability of uh, each number between 0 to 1 will be same, right? A coin pops out from the machine, we toss it, and it comes out to be heads. What is the conditional distribution function of the probability of head for that coin? Okay, so what does it mean? What are we supposed to provide? Okay, so this is quite important for this particular question to understand, because you have to understand what the question is demanding in this particular case, right? So if you see, what are we getting asked in this question? So we are asked the conditional CDF, the conditional distribution function. It is here, it is not cumulative distribution function. Okay, so it's conditional probability distribution of the probability of head for this coin. So thing is that, what is the probability that you get head given the uh, you have got a P, right? The probability of tails is P. Okay, so this is the question that is being asked. So this is quite an easy question, because this is the thing that you are being asked. So this will be just you can use the formula of conditional probability. This will be that you get head and y is lesser than P divided by P, y is lesser than P. So you have to take into account each possible P, right? And then you get a head. So that is your question. Now what is P y greater than less than P? So what is the probability that you get a P from the you get a number which is lesser than P in a uniform distribution? So it would be P itself, right? Okay, and now talking about the upper stuff, which will be obviously independent, because you are first getting a head, you are first getting P from the number, and then you are getting head. So it will be just simply P of head into P of y is less than P, then P y is less than. We have P over here, on the top we have P again, and the probability of head, of course, in this case is nothing but just a minute. So we have done a big mistake over here. This won't be multiplication, because obviously if you are drawing P, this head particularly is dependent upon your P, right? So you will be finding it using joint probability distribution. So it will simply be so basically, let us say you are getting a P out of kind of understand it like this. You are getting P from the uniform distribution, and then you are getting the probability of head, right? So the probability of tails is P, then the probability of head will be 1 minus P if you have got certain P from the uniform distribution. Then P I plus 1, then the probability of that P, right? And then so on. So multiple P will be there and the probability of head in that particular case. So it will just be integration of 0 to P dp and 1 minus P. So it will simply be P minus P square by 2. Okay, now you can put it over here. P into 1 minus P by 2 will be there, and then denominator the probability that y will be lesser than P is P itself. So that the answer that you will be getting is 1 minus 0.5 P. Okay, so to understand the question very it is very important that you understand the question. The question is very clear. So you have a penny producing company or a company that produces coin. Now it produces this particular coin that is there. It gives tail with a probability of P, but this P is not constant. This P is taken from a uniform distribution between 0 to 1. Now the question is asking what is the conditional cumulative distribution function of the probability of head for that coin. So this is the thing that is getting asked. So what is the probability of head given you get a P? So if you are, so what is CDF over here? Because this is cumulative distribution. So between 0 to P. Okay. So if you were given that it's y equal to P, then it's not CDF, right? So you have been asked y is lesser than equal to P, right? And in that case, you have been asked what is the probability to get an H. Okay. So that's as simple as. Now this question is you are given an urn with 100 balls. You pick balls from this particular urn one by one without replacement until all the balls are out. So you have 50 blacks and 50 white balls. You pick balls from urn one by one without replacement. Okay, that's clear. A black followed by a white or a white followed by a black is called a color change. Calculate the expected number of color changes if the balls are being picked randomly from the urn. Okay, so that's interesting. So let us say initially, so you have total 100 balls, so there will be 99 color changes, right? Sorry, there will be total 99 pairs, not 99 color changes, 99 pairs, right? The moment you take the first ball out, then second ball, then third ball, fourth one up to 100th, right? Now this will form one pair, this will form one pair. This can be a color change, this cannot be a color change, right? So you have to find out the number of color changes that may happen. Now let us pick any xi randomly, ith pair, okay? The probability that you will have a color change over there will be, the probability that you will have a color change over there will be, first of all, uh, try to understand it like this. Let us talk about the first pair. So you have 50 black and 50 white, okay? Now, the probability to pick a black is, the probability that you get a black is 50 by 100. And the next ball that you will be picking should not be from black, right? It should be from white. Then it will be 50 divided by 99 because there are total 90, and this can happen in other way around as well, right? Because so you can either multiply with 2 or you can write it like this. So this is the probability that you will have a color change over here, right? And if it will be a color change, then you can just simply this multiply it by 1. So if this probability was 1, then you will be having one color change. If this probability is 0, then you will be having 0 change. But if this probability is between 0 to 1, then you will be 1 into p color change over here. Now this can happen with total 99 pairs, right? We have total 99 pairs. So the x, let us denote x as the number of color changes, right? So we can write it as whether there is a color change at 1, number of color change at 2, number of color change at 99 pair. Now what I propose is that the probability that the color will change or there will be a color change at any random pair will be same, irrespective of whether you are looking at the 31st pair, 32nd pair, it will be same. Why is it so? Because there is a very logical reason behind it. The logical reason is that uh, try to understand that the ball is random, right? So the probability that there will be color change at 30 30th ball peak and 31st ball peak will be same as that of whether there will be color changes 90th ball peak or 90th one ball peak, right? So the probability that the color will change over there and over here will be same, right? Because the color change is dependent upon the balls. So try to understand it like this. You have placed a ball randomly in a circle. Black, blue, black, white, black, white, black, white. And now you can pick any pair out of there randomly, right? And then this probability will exactly be same. Okay. So if you place these balls at the circle, right? It doesn't matter whether you are looking at the probability of color change over here or probability of color change over here or probability of color change over here. This probability should be same everywhere. Okay, because the balls are placed randomly in this circle. So it does not matter whether you are choosing at which place. Now, if you ask me why a circle, it doesn't matter. You can break this circle at this point and still this probability should be same. That's why all this probability will be same. So basically it will be 99 into 1 into this 50 by 99 will be taken common and then 50 by 100 2, right? Or yes, so it is correct. 99 99 2. The number of color changes will be 50. Okay, so just think about this question and let me know if you don't understand the context behind the reason. Okay, so let us discuss this question. So you have a 12-sided die and okay, and you get whatever the die lands on. Okay, so if it will be 1 you get 1, if it will be 2 you get a 2, if it will be 3 you get a 3, if it is 4 you get a 4, right, and so on. Okay, now I give you an additional flexibility as well. So if you are unhappy with the roll, you can choose to roll another two six-sided die. Okay, so you get two chance if you want. Otherwise, you will be happy with the if you are happy with the first one, that's okay. So if the first time you roll a 12-sided die, if you are and whatever will be on the top, you will be getting that particular number. But if you are unhappy with the roll, what you can do is that you can choose to roll two sided die, and you will get whatever is the sum of these two particular dice. So how much are you willing to pay to play this game? Okay, this is quite an interesting question. Okay, so let us discuss it. So first let's start with the 12-sided die because this is the first die that you will be uh, rolling, right? Now, what is the average number that you can get? So what should be your expectation out of it? So your expectation should be 1 plus 2 plus 3 plus 4 plus 5 till 12 divided by 12, right? So what will be this number? I think this will be 55 plus 11 plus 12 divided by 12. This will be 66 plus 12, which is 78 divided by 12. So it will be 12 6 is 72.5, 6.5. Okay, so 6.5 is the average, and obviously it should be right. So 6.5 is the average of this number. Okay, now if your number that you are getting on the die, okay, is above 6.5, then probably you will not roll it again because take that number and you should be happy. But if it is lesser than the average, then you will want to roll this dice again. Not this dice, then you will take part in the two six-sided die, right? So that will be your strategy out of it. Okay, so how much are you willing to pay to play this game? So this should be the expected amount that you will be getting out of this particular game, right? So uh, obviously, so if you are getting on the die, if you're getting 7 8 9 10 11 and 12, then you probably won't want to play this game again, obviously, right? And then whatever will be on the top of the dice, you will be taking that and you will be going back. So the probability that you will be getting this 7 8 9 10 11 12 is again half, and in this case your expected amount that you are supposed to get is 7 8 9 10 plus 11 plus 12 by 2, sorry, by 6, right? This will be the average, plus with a half, right? With a half probability you will be rolling these two six-sided dice again, and in that particular case what will be your output, or what will be your average expected number? The average on first die is 3.5 and on the second die is 3.5 again. So the expected amount that you will be getting out of these rolling two sided dice will be just 3.5 plus 3.5, which will be 7. And finally, this is the total expected amount that you are supposed to get. And this is close to 8.25, I guess. Okay. So the strategy is simple. If first of all you will be looking at the average, which is 6.5. If you get above 6.5, you are happy with the two-sided die roll, and then you will be getting that amount and you will be going back. Otherwise, if you get something lesser than 6.5, you will be rolling the two dice, right? So again, the probability of these two events are again half and half, and then you will be just be multiplying with whatever is the average amount that you are supposed to get in these two particular scenario. Okay, so that's your answer. Now this question is very much interesting. You roll a dice until you get a 5. What is the expected value of the minimum value rolled? Okay, so you roll a dice until you get a 5. So you will be rolling your dice until you get a 5. So what is the expected value of the minimum value rolled? So try to understand it like this. You, for example, suppose your roll was like this, 4, 5. So you will stop here, right? And what is the minimum value till now? The minimum value is 4. Then you will roll it again. Obviously, because you want to do it again and again. For example, this time you got 5 in the first throw only, then you will stop and then minimum value is 5. Now you let us say your results are like this: 3, 1 and 5. In this case, what is the minimum value when you stop? It is 1, right? So now your task is to find the expectation of this particular value number. Okay, expectation of this particular number. What is the expected value of the minimum value rolled? Now note that you won't be getting 6 as the minimum value, right? Because let us say you got a 6 and then you got a 5, at which at that point you will stop. Then the minimum value will be 5 itself, right? Because you will be stopping only when you get a 5. So 6 can never be the minimum value. Okay, so this is something that you should note in this particular question. So now what should be the expected value, expected minimum value? Okay, so I would like to do it like this. Let us say 1 is the expected value, 1 is the minimum value, and then I will write probability that m is 1, and then I will say 2 is the minimum value, and then the probability that m is 2. Then again 3 is the expected 3 is the minimum value, and the probability that m is 3. And 4 into p m equal to 4. What does p equal to pm equal to 3 mean? Pm equal to 3 means that when you stop this game, the minimum value that you got is 3. Okay, till now. Okay, so that's deep. So, and you have to look at the probability. So you have to look at the probability. The minimum value is 3 when you roll these dice and when the game stops. So now let's start with what is p of m equal to 1. This should be interesting. So this question says that when you roll the dice, okay, again and again, uh, you are getting, when you stop, only one is the minimum value out of it. So that means 1 appears before 5. Okay, 1 appears before 5. So what will be the probability of this number, that 1 appears before 5? So there will be only two cases, right? One may appear before 5 or one may appear after 5. If one appears before 5, then the minimum value will obviously be 1. And if one appears after 5, then the minimum value will be, sorry, then the game stops, right? So that makes no sense. Okay. So in this case, the probability that the minimum value will be 1 is half. Okay. Sorry, it is just half. Now the probability that m will be 2, that is the minimum value will be 2. Now this is a bit complicated because you have now three numbers in consideration: 1, 2 and 5. Now try to understand it like this. If your minimum number is 5, if your minimum number is 2, then 1 must not appear, or 1 must appear after 5, right? So how many combinations are possible in 1 to 5? 1, 2, 5, 1, 5, 2, 2, 1, 5, 2, 5, 1, 5, 2, 1, 5, 1, 2. Now in this case, you are not looking at this particular case, you are not looking at this case, because here the minimum is not 2, minimum is 5. In this case, the minimum is 2, so you have to consider this particular case. Okay. particular case, the minimum is 1, right? So it's the case that you want to avoid. In this case, the minimum is 1 again, and in this case, the minimum is 1 again. Okay. So there are 6 possible scenarios, out of which only one is favorable, which is this one, right? In this case, 2 and 5 appears, 2 appears before 1 and 5 as well. So you have to look at a scenario where 2 appears before 5 and 1. So in this case, you see the probability is 1 by 6. So the probability that m will be 2, that is the minimum number will be 2, is 1 by 6. Now what is the probability that m will be 3? Now there are 1, 2, 3 and 5. These 4 numbers are racing against each other. And you expect that 3 should be staying away, 3 should be staying ahead of 1 and 2. So what are the possible number of combinations out of these 4 numbers, right? It should be 4 into 3 into 2 into 1, which is 24. And the case which is favorable for you is, what are the cases which is favorable for you? Think of this scenario. What are the cases that are favorable for you in this scenario? Pause a minute and then think. You will be having total 3 into 5 into 1 into 2. So you see like this. Okay. So this will be one scenario that is favorable, and the other scenario which is favorable for you is 3, 5, 2 and 1, or out of for 24, right? So they will be 2 by 24. So the probability that m will be 3, that the minimum value will be 3, is 2 by 24. Similarly, talking about 4, you will be doing like this similarly. 1, 2, 3 and 4 and 5. There are 5 numbers which are racing. Total number of events that are possible is 5 for the 20, 120. Okay. Now 4 and 5, this position is fixed. 4 should appear and 5 should appear, and 1, 2, 3 will be racing here. The total scenario will be 3 into 2 into 1, 6 cases, right? So 6 will by 1 by 20. So the total number of events in which 4 will be maximum, minimum is 1 by 20. And similarly, I want you to do it. The total number of scenarios where m equal to 5 will be 24 divided by 120. You can guess it. And the final answer will simply be 1 into p m equal to 1 plus 2 into m equal to 2 plus 3 into m equal to 3 and so on. I guess the answer should somewhere be 137 by 60, but I'm not so sure. Just calculate it and match your answer. Okay. Okay. So again, this is a optimal strategy game. These kind of questions are frequently asked by quant firms. Okay. And this question is this question is related to game theory as well. The question says that suppose two players are playing a game. The first player uh, choose an integer between 1 and 30, and again the second player picks a different one. Okay, that is there. So 1, 2, 3, 4 up to 30. After that, a random integer x is chosen from 1 to 30. Okay, so you are choosing a random integer between 1 to 30. The player whose number is closer to x gets paid x dollars. Okay, so whoever's number will be closer to x will get x dollars. So try to understand it like this. Let us say there are two players, right? So let us say the first player is a and the second player is b. So if a picks, let us say 16, and b picks, let us say 20. Okay, and the number that comes out is, let us say, 12. Now 12 is closer to 16, right? 12 is closer to 16. So in this case, A wins 12 rupees or $12, whatever it is, right? Because 12 is closer to 16. So now your strategy, the question that is asked is, would you first go first or second? And the second question is, what number would you pick? Okay, so that's the second question. Okay, so let us do it. So let us say A picks some number. Okay, so A is the one person who goes first. So A picks some number, right? Now, B has a choice to either go one step ahead of A, right? So if let us say A chooses 16, then B can pick 17 or 15, right? So that he at least takes advantage of all the possible scenarios, right? They cannot take ahead. So that's why B will be favorable. Either he takes one step below A or one step above A. So now let us try to find a scenario where A will be favorable or where B will be favorable, right? When he picks a number which is below, just a minute, let me change the setting. So let us say A picks N, okay? Now, if your A picks N, then what you expect is that, so let me write down an expression and then you will understand. Now, let me ask you what these numbers are denoting, okay? So you see what we are doing over here is that we are summing up all the numbers which is n plus 1, n plus 2 up to 30 divided by 30 in this case, right? And in this case, we are summing up all the numbers which are uh, from 1 to n minus 1 divided by 30. Now, what are we trying to do in this case? In this case, what we are trying to do is we are trying to pick a number, okay, above n, right? When we will be picking a number above n? When this summation is greater than this summation, right? If this happens, then what will if this number n and better let us say this is greater than this, then what will you be picking? What will B be picking? B will be picking n plus n 1, right? Why will B pick n plus 1? Because the expected payout when the number is greater than n plus 1 is greater, right? In this case, here you are having greater payout, okay? And if you solve this particular stuff, you will be getting n is lesser than 25.6. This will be the number, okay? So I think the number approx will be 25.6 lesser than n. Okay. So if player B wants to choose a number which is greater than n, right? If player B wants to choose a number which is greater than n, when will he choose a number greater than n? When will he choose n plus 1 and when will we choose n minus 1? He will be choosing n plus 1 when the expected payout will be greater by choosing one step above. Now, what is the expected payout in choosing one step above? So let me explain it this way. So 16 is there, right? Let us say A chooses 16. Then B either wants to choose 15 or 17. Okay. Now, when will B choose 17? Okay. So try to understand it like this. So if B chooses 17, okay, in this case, if B chooses 17, now what is the case? What is the expected payout for B? If the number that appears between 1 to 16, B will get 0. If the result is that the number is between 1 to 16, the result will be 0. And if the number that appears is between 17 to 30, then B will get a payout 17 up to 30 plus plus plus, and then you get divided by 30. That will be your expected payoff, right? Because 1 by 30 is the full of all these numbers. So this is the expected payoff in case B chooses 17. Similarly, if B chooses 15, right, then what will be the payoff for B? Expected payoff will be 1 up to 15 by if B chooses 15. Then the expected payoff for B will be 30 and expected payoff for A will be 16 plus 17 up to 30 by n. 30. And if you compare this number, whichever is greater, I think in this case, this number will be greater. Okay. So you have to find a number n. So what I'm trying to do is I'm expressing it in terms of n. So let us say A chooses some number n. Okay. Now B will either choose n plus 1 or n minus 1. I want to find out in which scenario B can pick n plus 1. Okay. Or B can choose n minus 1. So let us solve it, and if you solve it, you will be getting 21 minus 6 is greater than n. So whenever A chooses some number lesser than 21.6, let us say A chooses 21, then B can choose 22. Okay. So what does this solution mean? This solution means that the expected payoff. So let us say A has already chosen n. So A can choose a number greater than n, that is n plus 1, only when n is lesser than 21.6. If n is greater than 21.6, let us say if n is 22, A will have to choose 21 in that case, right? So what will B do? What will A do? A will first choose 22. Okay. Now if A chooses 22, what will happen? What is the expected payoff for A? Expected payout for A will be 22 plus 23 plus 24 plus 25 up to 30 divided by 30. Okay. This number will be, just a minute, let me evaluate it. 234 divided by 30 if A chooses 22. And for B, it will be 1 up to 21 divided by 30. And this number will be 231 divided by 30. Okay. And in this case, as you know, B will have to choose 21, right? In this case, B will have to choose 21 because if if n is greater than 21.6, that you already know, if n is greater than 21.6, then B will have to choose a number lesser than A, right? So in this case, if A chooses 22, B will have to choose 21. Okay. Now if B will be choosing 21, uh, obviously what they will have to do is that, because why are they doing it? Because this is the maximized payoff, right? Payoff is maximized as 21 or 20 at 21 or at 22. Now A will be choosing obviously 22 because the payoff is 22 234 by 30, and the payoff for B will be 231 by 30. So please remember that uh, this is not a question where you are asking at which number. So by choosing which number you will get maximum chance to win. Here the chance is that where you get maximum payoff. So A will be getting maximum payoff if he goes first and chooses 22 in this particular case. Okay, think about this particular question. This is quite interesting and I've explained in detail. Just think about it and then you will get the answer. Okay, so in this question again, you have a shuffle deck of 26 red and 26 black card. You play a game by repeatedly looking at the top card and either discarding it or ending the game. At the end, if the color of the next card matches that of the top card, you win, otherwise you lose. What is the optimal strategy? So in this question, I will give you a short task, but I will let you know the answer for this particular question. So the answer is simple, okay? The answer is whenever you have two cards remaining, two unseen card remaining, okay? There will be one card, there will be another card on top of it. You don't know what you are. So whenever you have two cards remaining, okay, and then all other 50 cards are like this over here. Now, since you already know what are the color of these 50 cards, and there will be one card on top of, obviously, on top of it. But since you already know the colors of these two cards, right? You know whether these two cards are of same color or different, right? Why do you already know it? Because you already know the color of these 50 cards, right? So you know what are the number of red cards out there and the number of black cards out there, right? Of 50. So you already know whether these two cards will be having same color, that is two red or two black. Otherwise, if whether these two cards are having different color. Okay. So now if these two cards are having same color, which you already know, then what you will be doing? You will be winning with a probability of 1 because you will be picking up the top card, you will be placing out of your barrier, and then this card and this card will have same result, right? So in this case, you will be winning with a probability of 1. So this is called two card strategy, okay? This is called two card strategy. Think over it. If these two cards are having same color, right? If these two cards are having same color, then you will be taking the first card out and then the color will be exactly same. Otherwise, if these two cards are not same color, right? If these two cards are not of same color, then what will happen? Think over it. So if these two cards are of same color, you win with a probability of half 1. So with a probability of 1, you win this game. Now, if these two cards are of different color, then what you will be doing? You will be flipping the first card. Then you will be checking whether it matches with the color of the card you have on the top or not. If it matches by luck, then you win. Otherwise, if it doesn't matches with the top card that you are having, then you lose, right? So in this case, with the half probability, you will be winning this game. So this is called two card strategy. Okay, and no matter whether you use any other strategy, in this case you are saying that you are having two cards remaining, and then that will be your win, right? So when you have multiple cards left, okay, when you have multiple cards left, then in that case this is not that will not be a good strategy for you to decide. So the optimal strategy for you to is to wait until you get only you have two cards remaining. So this will be the most optimal strategy. So if let us say you have n card remaining out of 52, try to see that if you have n cards remaining and if you flip at those cases and if you stop the game at that point, it this will not be the optimal strategy. Your optimal strategy would be to stop when you have two cards remaining. Okay, so think over this particular question. You are given two unfair coin, you flip both of them, and one's come head 2 by 3 time and the other comes head 1 by 3 of the time. Given you had a uniform prior on the bias before flipping, what is the probability that the first coin is more biased than the second coin? Okay, so you feel that both the coins were biased equally before you tossed these two coins, right? Now you got some event, you flip these coins. In the first coin, you get head with a probability of 2 by 3, and in the other coin, you get a head with you get head with a probability of 1 by 3. That is tail with a probability of 2 by 3. So now the question asked is that what is the probability that the first coin is more biased than the second coin? So this is a question that may get you confused because then what you will be doing, you have a prior distribution, right, which is that the both coins are equally biased 0.5, 0.5. Now what you will be tempted to do is that you will be using Bayes theorem to calculate the posterior probability that these two coins are biased with, right, by updating the results of the heads that you have got. But by just looking at the question, you realize that these coins will be equally biased because it is symmetrical problem. Right, coins are symmetrical, so you are getting a head with a probability 2 by 3 on the first coin and you are getting tail with a probability of 2 by 3 on the second coin. So by just looking at this symmetry, you will be saying that these two coins are equally biased. Okay, so as simple as that. So just don't get confused, otherwise using Bayes theorem will make this problem complicated. So the answer in this particular question will be half. Okay, in this question you do this task, you say that when you have R red and B blacks remaining, right, and you have n, so R plus B is n, and then you when you decide to stop at this particular juncture, see, just prove that this is either equally optimal as compared to the two card strategy game or less optimal than the two card strategy game. So no matter how much strategy do you design, it will either be equal to the in optimality with respect to the two strategy game or otherwise lesser than that. So the best strategy that you will be having is two card remaining strategy. Okay, in case you have any question on any particular solution, please feel free to drop a comment. Okay, thanks a lot.